on the coincidence of plus or minus 1 nanosecond with the other detectors. So here we can see this, here I've made like a timing selection around 0, and all these different humps are coming because the accelerator sends the electron bunches in 2 nanosecond offsets. So here you can see this delta timing, that's what these are. And also I can do some beta versus momentum cuts to make sure I'm getting proper pion, kaon, and proton. So here we can see the protons, and I make a cut around the protons. Here in the middle between the red, it would be the kaons, and I make a cut here. And then also for the pions, I make a cut. So now we can describe the vertices. So as I said, there was a butanol target, and then there was 2 carbon foils in addition. And so here we can see that this target is a fairly small target. It was only 5 centimeters long. And so we can make cuts around the butanol and the carbon to only get the events occurring within the vertex of the target. And then also, if we look at this schematic up here, this is in the center of mass frame. So here we have an incoming photon and the incoming proton from the target. When they interact, one of the final states that can be produced is the kaon in this direction, and then the hyperon. So in my case, this hyperon is the lambda or the sigma. So this gives you an idea of what the reaction would look like in the center of mass frame. So with all this in mind, as I told you, the lambda decays into proton pi minus. So then I want to make sure I'm getting the correct proton, because protons are created elsewhere. So I want to make sure this proton is really coming from the decay of the lambda. So what I can do is I can check the lambda decay by comparing the azimuthal angle of the proton and then the kaon. And so when I showed you the picture of class, there are 6 sectors. And you can see one, the 6 sectors in each direction. So here we can see that the proton and the kaon azimuthal angles are falling in opposite sectors, which was to be expected. And that's how we know we're getting the proper proton from the lambda decay. Okay, so even though we've done some calibration to the data, you still have to apply some corrections, because sometimes it's just not enough. So one thing that was done was I cut out bad time of flight paddles. So the time of flight paddles, there's 57 paddles in each sector, and there's 6 sectors. So this is just one example for sector 3. So what I did is I did the reconstructed mass of the pion, the kaon, and the proton. And what we can see here is there are these white stripes, and that means that the paddle was malfunctioning. So I just cut those from the analysis because the paddle was bad. So another thing, a correction that I did was there was a phi dependence of the missing mass. I'll describe the missing mass in a moment, but just so you can see already that there was, here's the 6 sectors of class, and you could see that there was this shift going on. And so that should be corrected. So we did a sector-dependent momentum correction. So here you can see that before there was a shift, and after the correction you can see that everything is really lining up quite nicely. Okay, so just some more corrections to talk about. So there was a timing offset in the time of flight, and that was due to a calibration issue. And so here is the run number on the x-axis, and in red we have the pions at 0, which is what to be expected. But for some reason the proton was not at 0, and they should be together at 0. So you can see, okay, they're not, so there was a problem with the proton. But then halfway through a little over halfway through the experiment, the change in calibration caused an even bigger offset. So then that can be seen here in this plot here. So here this plot shows the delta beta cut. So the delta beta is basically the measured beta minus the calculated beta. And in theory, you would expect that to be 0. Okay, well it is centered around 0, but here we have all these bands coming in, and those are basically misidentified particles. So after we corrected this timing offset, you can see down here, again this is for kaons only, you can see now that there's really only one stripe left, so that we really cleaned up our misidentified particles. And this over here, this is the delta beta cut for all the particles. And again, we expect that to be around 0 because we want the measured minus the calculated time of beta to be 0. Okay, so now the missing mass cuts. So I've identified the correct photon, kaon, and proton. So with all of that in mind, I can now reconstruct the missing mass. So I detected a kaon and a proton, and when I reconstruct the missing mass, what I end up with is this pion peak, and then we have a small hump coming here. And this hump is coming from the sigma decay, And so what I can do then is I can make a very loose missing mass cut from 0.05 to 0.3. And the reason I did this is so that I can then get the lambda and the sigma signals together at once. So then I can use this information to proceed to extracting my polarization observables. So you can see after I make a very loose cut, then I've kept the lambda signal and the sigma naught signal. So then I use this information to do background subtraction and also extract my observable. So now how do we extract the observable? So this is a formula for the differential cross-section. And the differential cross-section has all these different observables, and my observables of interest are T, F, Tx, and Tz. And they have different settings, such as the polarization of the beam or the target in addition. And so this polarized cross-section depends on many things. It depends on the polar angle theta, the azimuthal angle phi, and also the direction cosines of the proton momentum in the lambda rest frame. So then, with this formula in mind, it can be reduced to this formula, where the differential cross-section then is concerned with F observable, which I'm interested in extracting, and the T observable, again, which I'm interested in extracting. So here, this P lab is the polarization of our target. PC is the circular polarized beam polarization, because I'm using a circular polarized photon beam. And then, as I said, F and T are the observables I'm interested in. Now beta, as I mentioned, it's a transversely polarized target. So it wasn't polarized just in a perfect 90 degrees, it was polarized at a slight offset, around, say, 60 degrees. So this beta is referring to this target offset from the azimuthal angle. And then this phi here is the kaon azimuthal angle that's being detected. So what we can do with this cross-section is we can define a phi-dependent density function within each W and cosine bin. And so here we have this density function, and so we have some W is energy, and then also we have some cosine theta bin. Then what we can do is we can expand this density function in a Fourier series. Here is the expansion in a Fourier, so we have cosines and sines. And we can separate these cosine and sine terms due to orthogonality, and we end up here with some cosines and then some sines. So here there's a cosine in phi and then a sine in phi. And those are actually referred to as moments, and this is how we call the moment method. So now what do we do with these cosine and sine terms? So this T, target asymmetry, basically is a polarized target, but how do we actually extract it? So these sigma 1s and sigma 2s are related to the differential cross-section, and basically one could be one target setting and two would be the other target setting, because the target can be polarized in plus xy or minus xy direction. So that's how we can do this sum and difference of the two settings. And so then with these two settings, we can then just construct the final actual observable. And so the n's are basically some normalization factors. The P1s and P2 refer to these different polarizations I was mentioning of the target. And then the Z moments would be in the numerator, and that's referred to the sines. And on the bottom, we have the H moments, which are with the cosine. And so 1 and 0, that would be for the first target setting, but the 0th moment. So like here we would have cosine of 0, which is 1, for example. Okay. So now that we have this way to extract these observables, we need to do just some background subtraction. So other people in the experiment, they were using the carbon targets for background subtraction. But unfortunately, I really couldn't, because here you can see, these are my lambda and sigma peaks that I showed you previously. And down here in red, this is the reaction coming off the carbon. And so you can see the statistics are very small. And so when I tried to do a subtraction and normalize them to each other, it resulted in very high systematic uncertainties. So, and this is because this quasi-free kaon production is suppressed on carbon. So the way then I've done the background subtraction is I did a fitting procedure. So here is the lambda and the sigma signals, and what I did is I fit the signals to a Gaussian, and then the remaining background, I did a third-degree cubic polynomial fit, and then I made a combined global fit. And this I did varying a few parameters of the Gaussian, and then this was the resulting global fit. And I did this for every cosine bin and every W energy bin of my results. So this is just one small slice of all of this. So this is all of the events. There's no, anything bent, and this is just one sliver of my result, of the background subtraction. Okay, so now I'll just briefly talk about my systematic studies. So in an experiment, there are uncertainties involved with it, and this can be due to a variety of things. Things that I've done, such as the cuts I've made and the choices I made to vary things, and also there's just intrinsic uncertainties involved, like when we calculate, say, the photon beam polarization, the beam charge asymmetry, which has to do with the electron beam and the electron beam polarization. And I mentioned this target offset. Okay, we thought it's at 60, but is it really at 60? We're not sure. So all of these things have an uncertainty associated with it. And overall, as of right now, I'm not finished with these studies, but it's around roughly 11%. And so that is useful to then determine the results. So now I will show you my preliminary results. So the results, as I just said, they're all preliminary. And I'm showing you T, Tx, Tz, and F, and I'm showing you for both K plus lambda and K plus sigma naught. So the T observable as previously published results for K plus lambda. And then the previously published results are Graal, which was in 2009, and it was from an experiment in France. And then also Bonn, which was from 1978, and that's in black circles. So I'll show you that. The T measurement for K plus sigma naught is the first of its kind, and the same for Tx, Tz, and F are the first measurements of their kind for both K plus sigma and K plus lambda. And I'm comparing it to 3 theoretical models. The first would be the Kaon made, which is a model from around 1999, 2000 that hasn't been updated. And it's basically an isobar model using certain resonances to construct their models. Then we have the Bonn-Gacina theoretical model, which was updated in 2010, 11, and 12. And basically it's a partial wave analysis model using certain resonances. And then the final model I'm using is an RPR model, which is a Reggie plus resonance model. And that's done by the University of Ghent. And this person just gave me their predictions roughly a few weeks ago. So his are fairly current for him, or for their group. Okay, so first I will show you the target asymmetry T for K plus lambda. So as I said, the target asymmetry is for a transversely polarized target. So the red diamonds are this work that I've done. And so in blue is the Kaon made, in the magenta is the Bonn-Gacina curve, and the red dashed is the Ghent, the RPR. And so the Bonn data from 1978, it only has 3 data points. And it's these 3 black points right here. They were only able to get it at 0 degrees and in 3 energy bends. And as I said, the red data is mine. And the Graal data is these green dots. Maybe it's hard to see for some, I'm not sure. And it only goes up into energy around 1925 GeV. So most of these are bend in 50 MeV energy bends. And then there is 10 cosine theta bends. So you would think each plot would have 10 data points, but sometimes in the backward angle for Kaon photo production in class, that angle is not accessible, so there is less. So here at the lower energies, there's some discrepancy between my results and the Graal results. But as we go a little bit more in energy, you can see that the Graal results and mine start to have some overlap in the systematics. However, they do have large systematic error bars in their data. And then once we get to this point, there's nothing to compare it to. So these results would be the first of its kind as we go up. And then you can see that the models do have some agreement with the data, and but here, like at the very highest energy, no model really agrees with the data. So this was T for K plus lambda. Now I can show you similarly T for the K plus sigma naught. So again, this is the target symmetry, a symmetry with a polarized target. And so it would be the first of its kind. And here we can see that no model really agrees with the data. But maybe if we go a little higher in energy, the Bonn-Gacina, this magenta curve, starts to have some similar shape as the data. So that would be the T for K plus sigma naught. So now we have Tx. So Tx is basically a target asymmetry. So it's a polarized target, and this is the recoil polarization of the lambda in this x direction of the decay. And here we can see it again, it's the same curves, and it's bend in roughly 50 MeV energy bends. And again, there is no real agreement with my data in the curves, but I think that's okay, because some of the curves maybe are outdated, or maybe sometimes, for instance, in the higher energies, maybe my background subtraction maybe is not working properly, and that would need to be investigated a little more before these results would be final. And then also we have this target asymmetry Tx for K plus sigma naught. So again, it's this transversely polarized target, and the recoil hyperon. So here the recoil of the sigma in this x direction. And again, there's no data to compare to, and the models really seem to have no agreement. But I will admit, say for instance in this bin, there's only one data point. And I've thought about maybe why am I having more trouble with the Tx measurement, and that's because this Tx measurement is based on this recoiling hyperon. So if I'm not accessing the hyperon correctly, then of course then my result could be a little off. And this sigma, this is especially true for the sigma. For lambda, maybe it's not as bad, but when you go to sigma naught, it seems a little worse. And it could be because the sigma naught is decaying into this lambda and gamma, and maybe my lambda I'm not identifying properly. That could be one of the reasons. Then also we have Tz for K plus lambda. So this is similar to Tx. It has a transversely polarized target, but this is when the recoiling hyperon is in the z direction. So here we can see, again, there's no agreement with my data in the models. But again, it could be the models are wrong, or maybe sometimes, especially here, you would think maybe my background subtraction at the higher energies is not working properly and would have to be investigated a little more thoroughly. And then we also have the Tz for K plus sigma naught. Again, the same curves, no previously published data, and the curves don't agree with my data. And then we also have F. This is similar to the target asymmetry, but F, this is an observable that has a transversely polarized target, and then it has a circularly polarized photon beam, which as I said, for my portion of the experiment, I was using this. So I can access this F. So this is the F for K plus lambda, and here we can see there is no previously published data, and there's no agreement with any of the models. However, one thing I have kind of noticed is it seems that around this energy of 1775, there seems to be, it starts above 0, so it's positive, and then it becomes negative. And it seems to do this for quite a few bins. So I think that's something interesting to take away from this F result, is that there does seem to be some sort of a trend from starting in the positive and then going to the negative. And then when we get in higher in energy, the models don't agree at all with the data. And then finally, I have F for K plus sigma naught as well. And again, there's no previously published data. And I have the same models, but again, the models don't agree with the data whatsoever, which, that's okay. So, now I will make some conclusion remarks. And so, in conclusion, these new frost results will greatly add to the world database, which needs more kaon photo production. I previously showed you these 16 observables, and maybe 4 have been published actually. So there's a lot of work that can really be gained by publishing this data. And so it was the first result of its kind for Tx, Tz, and F for both K plus lambda and K plus sigma naught. And it's the first results of its kind for T for K plus sigma naught. And when you compare to Graal and Bond for T for K plus lambda, it shows some consistency. And the thing I didn't mention previously is that Graal did not have a polarized target. They used double polarization data OX and OZ to actually extract T. So they used some math representation combination of them. Whereas the bond and this current experiment actually had a polarized spin target. And so that's just something interesting to keep in your head that, okay, I don't agree with the Graal, but I do, at lower energies, but I do seem to have some agreement within error bars with bond, and they had a similar target. So the models will be updated to include this data, which then can constrain the models a little more. And also this data definitely has the potential to constrain partial wave analysis to find missing resonances, as I showed you this chart with all these yellow bars where the resonances are missing, or it can confirm other resonances that maybe have only been seen a little, so we can hopefully then make a stronger case for these resonances really existing. So, thank you.
At this point, we can entertain several questions from the audience before we start the usual examination. Dr. Kramer?
Natalie, could you show the slide that has the comparison of T for K plus lambda for Graal and bond?
Yes.
The results?
Yes.
Okay, so in that, I guess in some energy range, you have some overall resemblance to what the models predict. Is that what would say from that?
So this blue curve that Kaon made is a very old model, so it hasn't been updated in about 15 years. And this pink curve, the Bond-Gachina, it actually includes the Graal data, the green. So for sure the Bond-Gachina matches the Graal data because the Graal data is in it. For my data, what I find somewhat interesting is I do seem to have some agreement in the shape of the models. Do they fall precisely on the lines? No, but I would say they definitely seem to have the same trend and shape for T, not the other ones, but for T. So,
Also in this chart, the black dots are the bond.
yes, the 3 black dots are Bond from 1978.
And one more question
Yes,
on
of
this.
course.
Your error bars are much, as means the spread you got seem to be much smaller than either the bond or the Graal. Is that real?
So these data do not include the systematic uncertainties, so these error bars will grow a little, but I don't think they're going to grow like this. The thing with the bond, from what I understand, I wasn't around in 1978, but I did hear there was some issues with the experiment, and maybe there was, so that's why these error bars are so large. And I have a feeling the reason the Graal data has uncertainties that are so large is because they were really using this double polarization data to extract. They weren't accessing it directly as I am. They had to do some, hoops and jumps, and you can see that they don't have as, okay, I don't have the finest binning by any means, but I have finer binning than them. So I do have more statistics in general than them.
More questions from the audience? Well, if not, then we'll ask the audience to leave so that we can proceed with the examination, except for the members of the committee, of course. Thank you.
Thank you.